I take this privilege to introduce today's speaker, Parag Beeraka. Parag Beeraka is Director of Segment Marketing at ARM, where he is responsible for running different businesses within the IoT business unit. In his role, he is responsible for P&L of the business, along with product management, go-to-market strategy, and pricing strategy. Before joining ARM, Parag was responsible for the product management of embedded and removable storage products for smart camera, IoT, automotive, and mobile markets at Western Digital. Prior, sorry, prior to Western Digital, Parag also worked at AMD and Intel in various engineering positions. Parag has an MBA from the University of Chicago Booth School of Business. He also has a master's degree in computer engineering from University of Kansas. Parag is a Parag is a beloved alumni of VNR Vijnana Jyoti Institute of Engineering and Technology, where he received his bachelor's degree in electronics and communication engineering. He is an alumni student and student of Padmasai Ma'am for 1999 batch. We welcome you, sir, on behalf of ICMACC conference team. The session is over to you.
Thank you. Let me share. Good morning, everyone, and thanks a lot for the introduction. As Madam mentioned, I'm Parag and I work for ARM. I run segment marketing for them. So today I'm going to talk about engineering development paradigm shift to adapt machine learning on edge devices. So in this talk today, I'm going to go over initially with about what edge devices are, then go get an overview of what type of machine learning can you run on these edge devices, then really go deeper into the engineering development shifts needed and how can machine learning be embraced in this development flow. And my firm belief is that 10 years from now, pretty much every edge device that ships will have some level of machine learning in it already before it is shipped. So I think this is an important topic that needs to be addressed. And primarily because I do expect some of you to become future embedded developers. And this is something that will that some of you might have to drive as a paradigm shift. So with that, I think let's get started. So if you look at a very high level picture, you have trillions of devices that are generating data. These devices, you can see some of them here. It could be your phones, it could be your automotive vehicles, it could be your sensors, many of them. And these devices are currently making a lot of local decisions and uh, making either your industries run or even your hospitals run. But eventually, what we think is going to happen is these devices will generate massive amounts of data, and these will go to these edge servers that are in between either our wide network or even 5G or any other uh, wireless protocol. And then eventually, we do expect that critical data will move to cloud data centers where your data gets stored and analyzed. So, today, specifically, we're going to talk more about these trillions of devices that I'm showing here. So, this will be the focus of the talk today. So, let's take a step back and start first with basic understanding of an edge device. So I have listed a couple of edge devices here. An edge device can range from a sensor that is monitoring your energy grid, or to even cameras that are enabling smart cities, or as simple as temperature sensor even in your thermometer. Not so this is just the lower end of the spectrum. Edge devices, as we talked about, can also be more complex devices such as robotics like robots, and automotive cars, especially given the fact that some of the cars are doing automatic software updates to enable more features in the car. Moreover, edge devices are also available for different environments like environmental, farming, industrial, home automation, healthcare, IoT. So you can just see the plethora of devices. Furthermore, these edge devices can enable like various technologies like identity and tracking, virtual reality, augmented reality, smart lighting, etc. Moreover, they can also enable different verticals. Like you can see some verticals here, like building automation, retail, or even more complex industries such as transportation. Lastly, you see devices such as smartwatches, connected clothing. So you can just see the plethora of edge devices here, and even some simple things like coffee makers. And here you can see how we were able to map different attributes such as connectivity, upgradability, and high value information and performance across these edge devices. These are important, and this is where you will see how all of these features are really enabled by machine learning in the future as well. Now, the numbers here are specifically from ARM. So the numbers here, what you see, where till 2021, ARM has shipped 215 billion devices, and majority of them are actually edge devices that I listed in my previous slide. I can actually give a specific metric as an example as well. So currently, it's estimated that there are around a billion surveillance cameras installed, which is again an edge device. But the next billion cameras are going to be installed only in the next 4 years. So it's enabling these edge devices that actually is also a key factor that machine learning will become an important vector moving forward. And surveillance cameras is just one specific segment that I'm mentioning. So you can imagine this with sensors or virtual reality headsets and many other edge devices. So that's why you can see from many estimates that we can have around 1 trillion devices already installed with edge devices. So the bottom line is the future edge devices need to be intelligent, connected, and secure. Traditionally, what we have seen is edge devices were kind of installed once and forgotten. Let us take a simple example of a light bulb or a tube light that one of you might have installed in your home recently or the last few years. Pretty much once you have installed it, you kind of forget about it. But in the near future, we expect that these light bulbs or tube lights can eventually be controlled from an application on your phone in order to either turn it on or off. Now you can think about it and say, okay, do I really need to control my light bulb or a tube light from my phone? Maybe or maybe not. It really depends. However, if you take an example like an office place where, let's say, there are 1,000 employees, but on a certain day, there were only, say, 300 employees in the office, then you may not need all of the lights turned on. So the ability to remotely shut down few lights and save energy is, I think, kind of examples that you need to think through. And this is where it can indirectly save a lot of energy as well. And another valid example of this connected lighting and tube light case is something that happens in the West quite a bit, where people who go on vacations kind of turn it on and off to fake that people are still living in, so that they can deter the robbers who might have sights on the house. Another example I will give is people counting. The same, going back to the office example, if you can count the number of people in your office and adjust your air conditioning or heater systems accordingly, again, all goes back to saving energy. So capabilities to control your lights from your phone, people counting, these are nothing but intelligent devices which are enabled by using machine learning. So you can see the list of device, just actions here, where dumb devices could become smart, analog devices becoming digital, fixed function devices becoming reprogrammable, open devices becoming secure, once inaccessible devices becoming remotely manageable, and devices which were connected over Ethernet could become wireless so that they could reach areas where they couldn't reach before. Inflexible devices becoming autonomous, and raw data devices actually analyzing data on the device itself, and single sensors connected to multiple sensor fusion devices so that you can generate smart decisions. And last but not the least, any devices which were obsolescent becoming upgradable. So basically, what we are trying to say is future edge devices will be intelligent, connected, and secure. So you've seen kind of all the reasons why edge devices are much more valuable when they are connected and have processing capabilities. Here are just some statistics from various industry reports regarding edge device processors and their market potential with machine learning. You can see on the top left here, a report from ABI Research says that edge devices processors are estimated to be worth over $23 billion next year in 2023. Similarly, in the middle, you can see a report from McKinsey, which says that growth in AI-related semiconductors expected to be greater than 5x the growth in remainder of the market. Now, this is all great from the growth vectors point of view. I think the key important thing which we will talk about in the rest of the talk is the 9 million IoT and embedded developers that are there. So traditionally, we'll go over how development has been done and how they have to really change. Now, with the convergence of edge devices and machine learning, you can see the advantages here. More on-device processing in endpoints, which means these endpoints will have intelligence closer to the data. If you go back to the sensor example or the people counting example, you have the intelligence at the sensor itself so that you can make the decisions whether to turn on or off the lights. Similarly, significant growth of edge devices with machine learning is expected. There's a huge momentum in the ecosystem, and I can attest to this because ARM is a huge ecosystem player. We have millions of developers, and we can see really how many companies come to us to be part of the machine learning on edge devices. And lastly, leveraging scalable solutions to address diverse workloads is also important, because then only you can capture the market opportunity. A simple example I'll give you is going back to the people counting example. people counting example in a certain office can be very different if you want to install the same app on something somewhere outside. So that's why scalable solutions are really important. So let's now talk about specific use cases of machine learning in edge devices. And I often get the question from high-level execs like CTOs, COOs, and even CEOs sometimes. Can you tell us, hey, what are the use cases that machine learning can be enabled in edge devices? Because many people have heard about machine learning or AI, and many people are unclear on how they can enable their devices to be machine learning capable. So I think the way we answer this question is, I think you can imagine almost many use cases. However, we kind of put them in three buckets to just start the conversation. So here we have three areas. You can see vibration and motion, voice and sound, and then vision. So when talking to customers and partners about these relevant use cases, we start by explaining about the signal processing and machine learning inferencing that can be done. So signal processing, for example, applying filters before machine learning techniques for feature extraction and decision making. So let's go a little bit deeper into vibration and motion control. Just imagine being able to not only control a motor, but actually do predictive maintenance localized to the specific motor. These can apply to the millions of sensors monitoring industrial equipment around the world, or even temperature sensors if you have them in your home. You can just see the examples that we have listed here related to vibration, pollution, and many, many other use cases. Next, we have voice and sound. So think again, similar case where you can have one or several of your microphones to be used for keyword detection. We'll see voice in more and more places. So making a performance, cost-effective keyword spotting, we think is definitely a good idea. And this is where digital signal processing and machine learning actually need to work together quite a bit. And lastly, it's vision. And this is, again, I've given you an example of the number of surveillance cameras that are already installed. And this is actually one of my favorite topics as well, because this is really a case where customers really see the applicability relatively easily without too much explanation from our side. So let's take an example where you have your cameras installed in either a home environment or industrial environment. The capability to detect, say, faulty resistors or capacitors in an industrial factory instead of manual checking replaces quite a bit of manual labor, enhancing productivity. I think these are kind of use cases that are really, really getting applied as we speak now, actually. Now, all of these use cases have different workload performance requirements and, again, demand different solutions. So then we wanted to show what are the level of details of machine learning that can be applied to these edge devices. So again, here I'm not talking anything about the networks. I'm talking purely from a use cases point of view. So let's take the first one on your left where you see the vibration detection. So obviously vibration detection can be applied to sensors. Then you have sensor fusion and anomaly detection. And here I can give an example actually from company Amazon Web Services or AWS. So AWS has a service called Monitron or AWS Monitron that takes in data from multiple sensors that are connected to either turbines or water containers, and they monitor the data to look for inconsistencies using a sensor fusion gateway. And recently, a multi-billion dollar company like Baxter has been using this for the last few years. And with this usage, they've been able to save millions of dollars in predictive maintenance. Similarly, keyword detection can be applied to the same light bulb example, in which you can say with voice to turn off the light. Now, if you further extend to object detection, then you can imagine if there is some intruder in your house, then you can capture them in your surveillance camera. Now, some of the use cases may or may not be applicable to all over the world, which is fair. But I think our view was to give an overview of the capabilities so that you can imagine how it can be applied for your specific use cases. Moving further to the right, you can see examples like biometric awareness. So just imagine using your fingerprints for accessing confidential things on you, instead of using passwords. And you can see, obviously, a lot of phones have implemented this, a lot of laptops are implementing this. But imagine extending this to more and more edge devices as well. Then you have speech recognition. Imagine turning on or off your television using your voice, or specifically setting up your air conditioning temperatures using one specific voice. Then you have object classification and real-time recognition. This use case goes back to the example that I just mentioned in an industrial setting, where the capability to detect missing resistors, capacitors thus saves quite a bit of time, especially when you're producing millions of devices. Just imagine a phone manufacturer like Foxconn or someone who manufactures thousands of phones per day. Instead of having a person check, and if there's a computer vision enabled system that can check for defects, how much of money and time can they save? So you've seen the relatively high level use cases that I've mapped. Now, if you go back, we also talked about vibration, voice and language, and vision image as the three vectors. So I just wanted to also map something because it really has a broad range of machine learning applications. So specifically in vibration, you have sensor fusion, human activity recognition, and heartbeat monitoring as machine learning applications. Then in voice and language, you have beamforming, noise suppression, machine translation, speech synthesis. And for vision and image, you have movement detection, person detection, face detection. I just want to give some examples of each of these. So let's say you have a true wireless stereo or a headset that you have installed in your in your home. The probability that it's using beamforming, especially if it's a newer headset, is pretty high. So beamforming traditionally is pretty tough to do over regular CPUs. So that's why they've used DSPs. But with machine learning, I think they've been able to much better use beamforming for audio devices. Similarly, machine translation. Imagine yourself being in a country where you cannot speak the natural language there. Capability to either use your phone or some device to immediately do machine translation is actually an amazing thing. And lastly, let's go to the other extreme of super resolution. Let's say you've taken a video shot in a lower resolution, but you have a display or a television which is, say, 8K. Then the image or video needs to be enhanced. So over here, you can take networks that can provide super resolution and really scale the image, and your television will be able to easily showcase the image. On the right, I'm also showcasing the compute needs that are needed for these machine learning applications. So you can see on the right bottom, you just need tens of GOPS. But for a use case like speech resolution or segmentation, you can see that the compute hardware needs tens of TOPS. Whether you achieve this using a CPU or a GPU or a custom accelerator is up to you. But I think you can't match, you have to match an appropriate accelerator for the use case as well. So this is the last one from a machine learning point of view before we move to the engineering development flow. The other thing with machine learning is there are different developer personas as well, as some of you might know. First is an AI data scientist. So typically, this data scientist works in either research and development teams or universities. They publish new neural network architectures in papers or present them at conferences. So they are the ones who really create the networks. Mapping to the example that I mentioned in the previous slide. So a AI data scientist can come up with a new network for a super resolution use case. Then usually these networks are given to AI developers. So these AI developers customize these neural networks for specific use cases. And they usually work in engineering product teams. They also follow new trends and try to maintain best practices. They are also usually the one who can prepare training data by taking the network and then training the data so that they have a customized neural network for their specific need. Then the last is the application developer themselves. So this is the developer who is integrating these models into applications. So if you go back to the people counting example that I mentioned, so you will have influence from all these three personas for that people counting application. So the application developer develops the people counting application, for example, when to count, when not to count, how to detect dual people or multiple people. And the AI developer is continuously tuning the model to ensure the accuracy of the model is there. So you can see how the neural network development flow has different personas. Now, let me go into the crux of the talk, really. So we've seen the advantages and the new use cases that are enabled with machine learning, and how intelligent, secure, and connected devices can come into existence. So now one needs to take this newer technology and embrace it with devices that are already deployed in the field or devices that are going to be shipped in the future, the so-called edge devices that I mentioned to you in the beginning of the talk. Obviously, all of this is not free and easy. Interconnectivity and especially intelligence comes with a steep increase in complexity of the software. With the introduction of connectivity, multiple factors need to be taken into consideration while developing software, because security, over-the-air updates, networking, all of this become more and more important. If the device is using a operating system such as Linux or Windows, most of these issues are resolved at the OS level. But as you know, a light bulb is not really running a Linux operating system, right? It just runs a very basic real-time operating system. So for embedded devices, this is not always the case where you might have a rich operating system. So that's why engineers are required to manually integrate many libraries from different vendors and resolve the incompatibilities on the hardware. And this problem manifests even more considerably when security flaws are found and one or more components of the software needs to be updated. And obviously, time is critical. Devices need to be shipped because a lot of companies need to make revenue and hit their targets. So now if we add machine learning to this equation, then the requirements for updates go beyond security, because neural network models might have to be updated, refreshed based on the new data that is being acquired. And this is what we wanted to depict here in the chart on the right. We can't consider edge devices and machine learning as simple incremental change in complexity, especially on the software side. But indeed, it's a major disruption. So that's why you see the exponential curve on your right, where edge devices and machine learning have this steep complexity increase. And if machine learning didn't come into existence, then traditionally devices were getting more and more complicated anyway. But with advent of machine learning, you can really see the exponential increase in complexity. However, we do have a solution, and this is what we're going to explain in the upcoming talk. Before I jump to the solution, I did want to mention a little bit about the traditional embedded software development. And if you have taken any of your classes in basic digital communications or something, where if you're doing some sort of programming, then this might be relevant, or a microcontroller class, then this might be relevant for you. However, the vast majority of disconnected devices are already out there. Same going back to the light bulbs or your old cameras. They've already been installed and already exist there. Now, let me just walk you through what the philosophy of the software development was for these older devices. So let's take traditional example like a washing machine or a coffee maker, which has some level of electronics in them. So they've been flashed with a tested and validated version of the firmware, probably during the manufacturing process. And mostly the device doesn't have any internet connection or need the capability to be updated. So this is what we call deploy and forget. So the software team tasked to develop the software often moves on to a new project, and the functionality and security is probably frozen in time. So any software update that is needed is a massive effort, both in terms of testing, but most importantly for deployment, because it does need a manual process. Another aspect of the software team or the release engineer is control. There is, again, as we talked, there isn't any new firmware getting released or flashed into the device anytime soon. So most of the development is done either locally or in a local build environment, and testing would be limited. And because of the small attack surface, security is definitely an afterthought. So the assumption is that the device will not be compromised because, one, it's not connected to the internet and reaching the device is very tough. So this is how traditional older embedded software development was done for edge devices. So there was no machine learning, there was nothing. It was just a pure device which had some electronics in them. Once deployed, you could just forget about it. But in the new era that we just talked about, where you have edge devices which are intelligent, connected, and secure, we should really consider a different type of development flow. And this is the one that considers a close integration with services, both for data collection as well as training and deployment of machine learning models to the edge. So in this case, let's just start from the left. So we see data stored in the cloud or some other way for training of the network itself. Then the network needs to be going through a process of optimization, such as pruning or quantization, to reduce the size to fit the constraints of the edge devices. Just imagine a washing machine. It doesn't have tons of megabytes of RAM. It's a small device. Then the network model itself needs to be integrated with the rest of the software and packaged in a single image and finally deployed to fleet of devices. These fleets can be in single digit, tens or hundreds, thousands, or even millions of devices. And these devices in the field need to be monitored, and additional data may also be collected to improve the performance and quality of the neural network model. So as it's evident from this diagram here, the development practices like deploy and forget, not worry about security, will not work in this new paradigm. So that's why we have been kind of talking about a new style of development that I just mentioned called cloud native development. So this is the new paradigm to really develop edge devices. And as I mentioned, the edge devices are always intelligent, connected, and secure. Now, traditionally, development, especially engineering software development, has focused on application first, and then the building and the deploying of the software to these devices. However, cloud native development has the notion in a completely different way. Now, in this cloud native development, all the factors are considered from day one: machine learning training, over the air updates, security updates, managing devices. All of these factors are considered again from day one. So the cloud native technologies enable developers to build, manage, and run software in a modern and dynamic environment offered by the cloud. Now you can see here the software updates are deployed regularly. Small changes could be made very often. Continuous deployment, as I mentioned, is considered from day one. And there are other factors called DevOps and MLOps. MLOps stands for machine learning ops, where development environment is code. Automated tests are extremely important. Even the data scientists can update their models and the whole flow gets kicked in. And the most important part is security, and it's addressed throughout the full development lifecycle. So obviously, cloud native development is one of the new paradigms that we have been kind of embracing for the last few years for developing on edge devices. And I actually also wanted to show how it looks like when you put it all together. So this is an example of a cloud native environment by using companies like GitHub and companies like AWS. So you can see here, firstly, you might have a range of developers who are doing their local builds, debugging their code, etc. But when they are ready to integrate, they use a service from GitHub to merge their code into what we call the main repo. Then this will kick off some automatic builds and thus regression tests to ensure the code is safe to be deployed. The developer can review all the verification results and tweak if needed. And as I mentioned previously as well, the ML developers also can be tweaking their models, etc., all the time. And once they are done, their changes are also sent to the cloud repository. And it goes through the same final checks and balances. Finally, when the code is available, it gets deployed into multiple devices. Again, as I mentioned, these devices can be single digits to hundreds to thousands to even millions. And there is a loop back from the devices to retrain the models. So you can see how cloud native development is very, very different from the traditional embedded software development that has been practiced over for almost 30 years or so. Now, however, there are a couple of complications. Unlike cloud applications that are run for either networking or storage, it's tough to run many IoT applications across just virtual machines because you do need real hardware. First of all, as you come into the industry, you'll notice that it's obviously tough to scale hardware. Not many companies in the world ship millions or billions of devices. That said, IoT boards or edge devices boards and chips are relatively cheap. Building and managing board farms is doable. There are even services from companies who can enable you to do this. And at the same time, there are many other types of example applications such as virtual hardware or models that can be used to simulate your hardware. So instead of trying to deploy to hundreds of devices for testing, you can use models or virtual hardware to really test these devices. Now, before I move, there are two other things that I wanted to make sure everyone is aware of with respect to edge devices, and they are security and what I call interoperability. Because a single device that is not secure can compromise the entire network. And as you can see here, security attacks on edge devices continue to get more sophisticated and cheaper to perform. All edge devices need to implement the following security services to be really, really secure. They have to be uniquely identifiable and support a security lifecycle as soon as they come out of the factory or even during the factory manufacturing. We need to make sure that these devices are really secure, because imagine some sort of a malfunction firmware being installed into these devices. So edge devices need to be securely attestable, which means that the trustworthiness of a device must be established. Similarly, edge devices can only install authorized software, which means that there cannot be capabilities to support any sort of anti-rollback. They have to support secure updates. They have to support trusted services. And obviously, all of the firmware needs to be in secured storage. So the other feature that I also want to mention is interoperability. And this is an example that I have here from Connectivity Standards Alliance. They've recently published a specification called Matter. Just imagine having devices from multiple companies, but they not working together. So Matter really solves that. So as an application developer on an edge device, you really need to think through, okay, how can my device talk to other devices as well? And again, you have the same machine learning, security, and all these capabilities. So as you can see here, these edge devices are really getting way, way more complex. All right, so this is one of the last ones here. Here again, you can see some couple of companies like AWS, Amazon Web Services, and Microsoft Azure. They already have a lot of services for cloud native development for edge devices. I'll just go over one example here. Like if you take Microsoft Azure, you can see the different sensors and IoT devices. So when they generate data, they're saved in data lake storage. They can use Azure ML, and at the same time, they can also use different databases like Cosmos DB and really create full applications on top. So these are just examples of companies that are really embracing cloud native development, because obviously they have the inherent nature to support. So to summarize, machine learning is going to really go and become an integral part of future edge devices. So these edge devices, again, will be intelligent, secure, and connected. The practices from an engineering development point of view on these edge devices will have to really adapt to embrace machine learning, and on top of it also embrace security and interoperability. So thank you so much for this opportunity, and yeah, that's all.
Thank you, sir. So, any questions from student side, participants, online participants also? One question, sir. 1 minute.
Hello.
Yeah.
You said something about matter when you were discussing about the interoperability. Would you like to expand a little more about it and the functional developments that are happening in the recent past with regard to the matter alone?
Yeah, sure. So I think simple way to think about it is, let's say you bought a device from Google. Google sells like Nest cameras, at least here in the US and some parts of the world. And let's say you also bought a Amazon Alexa device. Now, these two devices currently don't talk to each other, or there's no easy way for them to talk to each other. You need to install some other third-party application and make sure they are all talking the same language. So Matter really solves that problem. So a Google Nest device can talk to an Amazon Alexa device. So as you can see, I don't think I went through the details in that picture. It runs on top of Wi-Fi BLE, which stands for Bluetooth Low Energy, and Thread. So these are the layers, and then on top you have TCP and UDP, and then on top it's really like an L3 protocol, if you remember your network stack. So it really is to maintain interoperability. So many companies have started to enable Matter on their devices. And in the future, we expect like all devices will ship by default having Matter support. So this is really what Matter is about. And it's all open source, by the way. It's a bunch of companies really working together for interoperability, because as I mentioned, connectivity is super important. But if your devices are not able to talk to each other, then you're limited in the number of use cases. So with this, I think you can enable much more complex use cases and benefits.